Hey everyone, the lecture I have for you today is on Unit 7.2 in AP Chemistry, which is called Direction of Reversible Reactions. So we're just going to go over a little bit more about that equilibrium arrow that we talked about in the last lecture, so let's just jump right into it. If you want to pause the video and read these, I encourage you to. This is what you should be able to do by the end of Unit 7. So if you can do this, you should be perfectly fine for that part of the AP Chemistry exam. So I just want to start off going over again what a reversible reaction is. So a reversible reaction is a reaction that can go from reactants to products, or it can go backwards from products to reactants. So the way that we draw this in chemistry is, let's say that you have a reactant A, and that reactant can reversibly go, so this is called an equilibrium arrow that I just drew, can reversibly go to a product B. That means we could go from A to B, which is considered the forward reaction, or we go from B to A, which is considered the backwards reaction. And that forward and backwards reaction have different rates. So the way we would say that is we would say you have the rate of the forward reaction, which is K forward, the rate constant for the forward reaction. And then you also have rate backwards, so you can have KB, which is the rate of the backwards reaction. So when a reaction finally reaches equilibrium, and this is what we talked about in the last lecture in my class, is that when it reaches equilibrium, those forward and backwards rates are equal to one another. It's not that the reaction has stopped happening, it's that we're not making any more reactants than we are products, because we're having a reversible reaction happen back and forth. So one other thing I need to point out about rates of reactions is that at equilibrium, rates are equal, the concentrations are not equal to one another. So the reaction I have going on here is I have N2O4 breaking down in a reversible reaction into two equivalents of NO2. So let's look at both of these graphs and see what's different about them. So the graph I have on the left is a concentration versus time graph. And what you can see is we start off with a bunch of N2O4, we start off with no NO2, and the N2O4 is breaking down into NO2, so we're losing concentration. Well, if we're losing N2O4, that means we have to be gaining NO2, so that's going up. But look at what happens right about here at this dotted line. You see that we're not changing the concentration of NO2, we're not changing the concentration of N2O4. That means that we've achieved equilibrium. And what you can see is the concentrations here are not equal. The rates are, because we're not changing concentration anymore, but the concentrations themselves are not equal to one another. However, on the right side over here, I have a rate versus time graph. And what you can see here is that the rate of the NO2 is going up. So this is rate as we go backwards. Okay, so in other words, maybe I should write this on here. In other words, this is the Kr, the K reverse reaction, or what I wrote on the last slide is Kb, K backwards reaction, and this is the Kf. So as you can see, the rate of the forward reaction is getting slower and slower and slower, and that's because we're losing our concentration of N2O4. But the rate of the reverse reaction is getting faster and faster and faster because we're gaining more of this. And if we remember from Unit 5 in kinetics, as your concentration increases, your rate increases. So if we increase the amount of NO2, we increase the rate. But what you can see is when we hit equilibrium, it's not the concentrations that are equal, it's the rates of the forward and backwards reactions that are equal, and that's so important. The reaction doesn't stop, it's just that the rate of the forward and rate of backwards are equal to one another. And something we also need to know about this is that almost always one direction is favored. So for example, if the Kf, the forward reaction, like we said in the last slide, is favored, then it's going to be bigger than Kb. In other words, we're going to have more products at equilibrium than we're going to have reactants. If the backwards rate constant is bigger than the forward rate constant, well, then we're going to have more reactants than we have products. And very rarely it happens, but sometimes the Kb and Kf are equal to one another. In that case, both reactions are equally favored and the products would be equal to the reactants. The only example that I'm currently aware of, I'm sure there's thousands of others with as many chemical reactions as there are, but the only one that I'm currently aware of for this class that you need to know is esterification and hydrolysis, making an ester or breaking that ester back down. Another thing I want to point out about when I say something is a favored reaction, Another way you can think about something being favored or a reaction path being favored is that it has a lower activation energy. So if we look at this, if we remember from Unit 5, this is what's called a reaction progress diagram. And so you have a potential energy curve right here, and you have reaction progress. You can also see this as reaction profile. And you see we have the reactants, the transition state, and then we have the products. And what you can see is the energy of activation, the energy to get from the reactants to the transition state is lower than the energy it takes to go from the products to the transition state. So what's going to happen is it is going to be easier for the reaction to get over this hump right here than it is for it to get over this hump. And so the reactants are going to go almost all the way to products because it is favored going this direction. In other words, the direction that has the smaller activation energy is the way that's typically going to be favored. And so like for an exothermic reaction, and we know this is exothermic because the products are lower than the reactants, the forward reaction is going to be favored. It is easier to go over this hump this way than it is to go back over the hump this way. Now, a common question that you get asked on AP chemistry tests a lot, and a lot of AP chemistry teachers like to ask this, is do catalysts do anything to change equilibrium? So we talked a lot about things from Unit 5, but what do catalysts do? And the big answer to this is a catalyst has absolutely no effect on the equilibrium, and here's why. So if I have another reaction progress diagram, reaction profile diagram here, what you can see is I have the reactants right here, and I know my face is kind of blocking it, but the products are over here. So what you have going on is that we have an uncatalyzed reaction, so no catalyst in the reaction. That's the blue line right here. And it's still an exothermic reaction because the products are lower than the reactants, but this is how much energy it would take to get over for the forward reaction, and this is how much it would take to get over for the reverse reaction. Excuse me. If we add a catalyst in, what a catalyst does, it gives me a different path that changes the activation energy. And so this right here, this red line, or I guess this pink line here, is the forward and the reverse of a catalyzed reaction. And what you can see is there's a change in activation energy. Remember that little triangle? That little triangle is called delta. It means the change in activation energy. Both the forward and reverse reactions get the exact same change in activation energy. In other words, they both benefit by the same amount. So it doesn't actually change the position of equilibrium at all. Catalysts speed up the reaction, but the equilibrium position is still the same. This slide right here is usually pretty important for chemists because of something called Le Chatelier's principle. We'll cover that in a much later lecture, but for right now, this is kind of an introduction to Le Chatelier's principle. So what this chart is, it tells you what causes more reactants or more products to form in equilibrium. So you've now learned what equilibrium is, but one question a lot of my students always ask is, well, can you change that equilibrium? And the answer is yes, in different ways. And you can also manipulate a reaction, or you can stress a reaction's equilibrium. And so this is a lot of different stresses that can happen to a reaction that is at equilibrium. And so let me kind of explain what's going on here. So the stress for this reaction, this says what happens if we increase the concentration of A. In other words, this red line right here, that's the stress right here. Okay, that's the stress. So if we increase the concentration of A, well, what happens is our equilibrium actually gets shifted over to the right. In other words, we end up producing more products if we give more A to the reactant side. If we increase the concentration of D, which is on the product side, so we increase the concentration of D, we actually push the reaction this direction. We end up creating more reactants. If I decrease the concentration of B on this side, well, I now want to make more B because I decreased the concentration of it. I want to make more. So I'm actually going to shift towards the reactants to try to make more of it. If I decrease the concentration of C, same logic. I want to make more of it because I decreased it. So you can see my equilibrium arrow is pointing more this direction. If you decrease the pressure, this is something we'll get to in a later lecture, but you just may want to take note of this and kind of look over what's happening here with the volumes. Also, increasing the temp is something we're going to get to in a later lecture, but again, what I said about a catalyst, there's no shift if you add a catalyst whatsoever. So I just want to do this quick thought experiment right here, this quick problem together, and then I'll be done with the lecture. So this question says the reaction N2 plus 3H2 yields in equilibrium. Now I know that doesn't look like an equilibrium arrow, but you know the limitations of PowerPoint. Goes to 2NH3, is at equilibrium at 500 Kelvin. What happens to the rates of the forward and reverse reactions if some NH3 is added at time t? Well, what happens to the rates of the forward and reverse reactions? Well, we just added more NH3, right? So we added more of this guy, okay? Well, if you add more NH3, the equilibrium is going to shift this direction. This right here is the stress. That's the stress that we just put on it. We increase more NH3. So we're going to go that direction, okay? Well, if we go that direction, that is the reverse reaction, right? So by increasing the amount of NH3 that we have, you are going to increase the rate constant, or you're going to increase the rate of the backwards reaction, and you're going to decrease the rate of the forward reaction, okay? Because the stress you put on is you added more products, so you're going to want to make more reactants. All right, well, that's everything that I have to say here. If you have any sort of questions, please don't feel free to leave those in the comments. You can send me an email about it. I'm happy to help with any of that sort of stuff. But thank you guys for watching. Thank you guys for listening, and I'll see you guys next time.